Hello, everyone. My name is Tracy Hartledge. On behalf of Chiral Technologies, I want to welcome you to our presentation, Implementation and Utility of Daicel sub-2 micron chiral stationary phases for ultra-high pressure liquid chromatography. Presenting today is Dr. Weston Umstead, Technology Manager. Dr. Umstead graduated from DeSales University in 2011 with a BS in Chemistry and Biochemistry, and from the University of Denver in 2016 with a PhD in Chemistry. Dr. Umstead has been with Chiral Technologies since 2016, where he started working in our Definity Genomics group on the development of fast and reliable PCR cleanup products. Now, as the technology manager, he is responsible for new and emerging technologies, Definity Chemical Services, and the core technical team, who are responsible for our in-house chiral screening and separation services. During the presentation today, members of our technical team will be on hand to answer questions you submit through the presentation dashboard. Please click on the Ask a Question button, and you can write in your questions and receive a written response. Please feel free to reach out as questions arise, or we will also be having a Q&A session following his talk. As always, you have the option of reaching our technical support team by emailing questions@cti.daicel.com at any time. Please note that a copy of Wes's presentation is available in the handout section of your menu. Along with the presentation, we have included information on our column selection service and application notes on our sub-2 micron columns. Enough from me. Please give your attention to Dr. Umstead. He will take over now. Wes, the floor is yours.
All right, good afternoon, everyone, or good morning, depending on where you're located at. I appreciate your introduction, Tracy. And so as you are all probably aware, we are going to be talking today about Daicel's new sub-2 micron chiral stationary phases for ultra high pressure or ultra high performance liquid chromatography. So to begin, here's just a very brief outline of the different topics that we're going to touch on. I think it's important that we start off with an introduction on chiral chromatography. Some of you may or may not be familiar with some of the background in terms of the mechanisms for selection and how chiral chromatography works in general. So we'll start off on the same page regarding that. We'll then do a very brief history on UHPLC and the theory behind sub-2 micron. We will do some things that you need to consider when you're going to be implementing sub-2 micron and using UHPLC, and then we'll end with a lot of different examples using Daicel's new sub-2 micron columns. So to start off, just a very general background on chromatography. There are three different components to any chromatographic system. Obviously, you have your column, you have your instrument, and then you have your chromatographic conditions, your mobile phase composition, additives, things like that. Now, each of those components has a set of unique parameters that kind of affect its overall performance. So for instance, the conditions are controlled by the mobile phase composition. The overall length of the system is controlled by the column, or is related to the column. And then the instrument can only perform as well as the sampling rate of the instrument is designed to sample. So in some cases, though, there are multiple components that can be affected by the same parameter. So for instance, pressure is related not only to the length of the column or the particle size of the column, but it's also related to the actual conditions. So a higher viscosity mobile phase naturally gives you a higher pressure. And in some cases, actually, a component or all three components are affected by the same parameters. So your overall analysis time is affected by your sampling rate, the length of your column, and the strength of your eluent for the chromatographic conditions. So if you look at all of these things put together in kind of a triangular Venn diagram, as it were, you can see there's a number of different terms, as I mentioned, that are unique to just each individual component, but you've got some over here, selectivity, for instance, which is related to the column and the chromatography. And then right smack dab in the middle is resolution. And the resolution is not only affected by the three components of the chromatographic system, it's also related to N, which is the plate count, and that is directly related to the particle size. And so that's why we are here today. We're here to talk about particle size and how using sub 2 micron ultimately increases the number of theoretical plates, and as a result of that also ends up improving your resolution. So if we look at particle size development over the last few decades, it's been something that has been continuously evolving essentially since the inception of chromatography early on. So in the 50s, uh, the best that the industry had to offer were irregularly shaped particles that were 100 micron or even larger. And if you tried to pack them in a column, you're looking at maybe 200 plates if you're lucky. When HPLC kind of started in the 60s, in the late 60s, we were dealing with 10 micron as we wanted to try to improve our resolution and improve our efficiency. We were able to get smaller 5 micron particles, and you were also able to get more symmetrical, consistently shaped particles, which helped with column packing. You're probably all aware of superficially porous particles, so they came out in the late 90s, early 2000s, and we began to move into sub 2 micron right around when UHPLC was launched in 2004, with sub 2 here in 2003. And the biggest improvement, as I pointed out already, is in the number of theoretical plates. So we were at 200 plates early on. We can now achieve things up to 32,000 or even more depending on the particle size and the efficiency in terms of packing. So Daicel, back in the 80s, when Daicel acquired this technology of polysaccharide chiral stationary phases from work that was done by Professor Okamoto from Japan, we started developing stationary phases on the particles that were most reliably available, which was 10 micron. And then we slowly progressed into 5 micron, 20 micron for preparative scale, 3 micron, and now we have obviously our sub 2 micron particles as well that we'll discuss a little later on. Initially, a lot of the work was focused on the chiral selectors. And so if you go back to Professor Okamoto's original work, there's a number of selectors that were there. And now we're obviously starting to look at how can we make our products a little bit more applicable to the market and reacting and being preemptive in the types of demand that's coming from you, the user. But if we look at the chiral selectors, this is just a screenshot of some of them from our chiral selector poster, which is free. If you go on our website, there's a link there that you can get one of these sent to you yourself. But we have 39 different chiral stationary phases. And of those 39, there are 34 unique selectors, 5 of which are available in coated and immobilized versions. So if you look, for instance, here at IA is 3,5-dimethyl triphenyl, 3,5-dimethyl phenyl carbamate. It's the same selector as AD, except AD is coated amylose, and chiral pack IA is immobilized amylose. And so I already made the distinction. You've got amylose and cellulose. In yellow here are your cellulose-derived stationary phases, and in blue are your amylose-derived. That's important because, for instance, if you were to screen a compound against IA and IB, although they're the same selector, you oftentimes will see very different selectivity or separation ability depending on your compound. And so what is different? Really, you're talking about the difference in the linkage between the individual glucose units. So for cellulose, you've got a beta linkage between the different subunits, and in amylose, you've got an alpha linkage, which doesn't necessarily seem like it's that large of a difference, but when you actually look at the separation ability, as I said, you can see in some cases separation on one and not the other, or separations on both. So in order to determine what selector you actually need, we generally will apply a brute force screening approach where we will take a number of different selectors, our chiral pack and our chiral cell selectors. We'll screen it on a number of different mobile phase combinations: normal phase, reversed phase, polar organic, extended range, which is basically an extension of normal phase, except they are mobile phases that are not compatible with our coded columns. So the first generation of phases listed here are your ADs and your ODs. O's for our chiral cell, or O being for Professor Okamoto, so a little bit of homage to him there. And then our ADs and whatnot of our amylose phases. These phases can be, they're just coated on the silica gel surface. And so things like THF and dichloromethane will actually dissolve the polymer off of the silica gel. So those are your extended range solvents. And then you've got your immobilized second generation, which these are resistant to that same effect with THF and DCM and whatnot. So these can be used in those extended range normal phase conditions. And we also have a number of specialty selectors as well, which we really won't touch on in this presentation today, but we have the protein phases, your AGP and your HSAs. You've got your ligand exchange, your crown pack, your crown ethers, your Lindner phases, as well as the relatively recently developed zwitterionic Zwick's phase. Now, the reason we have so many, as I said, there's really no good way to predict what the interaction on the column is actually going to be, and that's because you've got a large number of possible chemical interactions that can take place, electronic interactions that can take place. This is just a very short list of some of those. When we're dealing with chiral chromatography, most often we're talking about hydrogen bonding, steric hindrance, pi-pi interactions, and dipole-dipole, either induced dipole-dipole or dipole-dipole from some interactions within the molecules themselves. So if you look at just kind of a sample, this snippet, this would be a cellulose backbone here, and based on the chiral selector, this is actually OC stationary phase. You can see that there are a number of different possibilities for interactions. You've got the amide here, so you've got your carbonyl and your nitrogen, which can hydrogen bond. You've got your phenyl group, which can pi stack. And then when you actually have this polymer coated on the surface, the polymer doesn't just exist as a linear form, it actually twists on itself, and so you end up creating these chiral grooves, which then adds a secondary level of interactions, which makes it even more complicated in trying to predict which stationary phase will work for which compound. So I'll touch on these chiral grooves in a couple of slides here, but you can see it gets more and more challenging as you actually look at the structures of these compounds. In general, though, what we like to use is what's called the three-point interaction model. This particular example here, this Eason-Stedman model, is designed more for chiral drug interactions with a drug binding site, but it illustrates the same principle that you have your drug binding site, or in our case, a chiral stationary phase, which has 3 points of interaction. And then you have your active enantiomer, and then your inactive enantiomer, or in our case for chiral chromatography, your active enantiomer would be the more retained enantiomer. Your inactive one would be the one that kind of comes through quickly. You've got the points on your compound which line up well with the interactions on the stationary phase. And so this active enantiomer, this more retained enantiomer, interacts with the stationary phase differently, and they elute at different phases, different times. With your inactive enantiomer, obviously here you can see that everything doesn't line up perfectly, so it's not as strongly interacting with the stationary phase, and even if you were to rotate it, you still have a mismatch, and so it ends up eluting faster as a result of that. This is a little bit more of a bulky diagram, but it represents basically the same thing. This was from a review article done by Professor Lammerhofer, and probably a little bit more representative of what is actually going on in the system. You've got your chiral selector, which is solvated by whatever your solvent is, and you also have your enantiomers, which are solvated to some degree, depending on their interactions. And in your ideal fit bound state, as things are kind of coming through, your solvent is displaced, and your active enantiomer, in this case your S enantiomer, is interacting strongly with your stationary phase, and your non-ideal R enantiomer is only interacting perhaps in one location and still solvated in some other. So you kind of get the point. 3 points of interaction is desired for a good recognition on your stationary phase. So if we go back to the chiral grooves, which I mentioned before, this is the same selector. This is our phenylcarbamate. So this is OC, cellulose, and then it's the same selector on amylose. When the polymer itself actually twists, you've got these chiral grooves. In cellulose, it happens to be a 3/2 left-handed twist, and in amylose, it happens to be a 4/1 left-handed twist. And so depending on how your compound can actually come through and interact with these different grooves, it will determine how strongly or not strongly it interacts with the stationary phase. And here's where you can illustrate the same selector has the possibility of having different interactions with the polymer because there's a different number of twists. So if you look at something like prilocaine, prilocane's got 4 predominant interactions that it can have with the stationary phase. You've got hydrogen bonding, pi stacking, dipole-dipole stacking, and then steric inclusion. And so again, if you're looking, this is OC, we're actually going to look at our newer phases, our immobilized phases. If you were to do a screening on normal phase, so hexane IPA with 0.1% DEA, since this is a basic molecule, if you were to screen this on IA, so IA is our 3,5-dimethyl phenylcarbamate on amylose, you really don't have any separation. You're getting a little hint of separation here. Your alpha is 1.04. Alpha of 1 is considered separation. Alpha of 1.2 is baseline separation. So you're not there at all. If we were to keep the same selector but change to cellulose as the backbone, now you're starting to see pretty good separation. It's not quite baseline yet, but then if you take it one step further and change the electronics of the selector from 3,5-dimethyl to 3,5-dichloro, which is IC, still cellulose, now you have a very strongly retained pair of enantiomers. So you're going up almost to 20 minutes versus 10 minutes or so in your IB and your IA cases. Your alpha is 1.25, so very good baseline separation. And all by changing the polymer from amylose to cellulose, and then changing the electronics from from methyls to chloros. And so you can't really model this. Again, it goes back to the point I made when I first started this. You kind of have to employ a brute force screening approach in order to see what combination is going to work best for the compound that you have. So if we move on then, that's our basic introduction on chiral chromatography. If we move on to history a little bit, it's a very brief history for UHPLC, primarily because the first commercial systems were only launched in 2004. So there hasn't been a whole lot of work done yet to this point. But the first important point to make is there is no difference between UHPLC, UPLC, and HPLC. In terms of the technique itself, all 3 of these things are exactly the same. They're all liquid chromatography. The pressures are obviously different. Your ultra high pressure, high performance systems are intended to be used at higher pressures, but it's the same mechanism for separation. And there's no difference between UHPLCs and UPLCs. They're both ultra high performance liquid chromatography systems. It's just a difference in the way different manufacturers began marketing their systems. UPLC is a Waters name. UHPLC is generally referred to by the other manufacturers. Now there have been additional steps taken between HPLCs and UHPLCs to minimize the effects of extra column band broadening, but that has more to do with the actual chromatography, not necessarily the systems themselves or how they perform or how they function. So the particle sizes were advancing, but the instrumentation was not. I went through the particle sizes already. The pressure limits for HPLCs were pretty much stagnant at 400 bar from their first commercial launch in the late 1960s until the early 2000s. As I mentioned already, Waters was the first to launch a UHPLC, their UPLC acuity system. That could achieve pressures of 1,000 bar, which was a remarkable step forward and allowed now people to use sub 2 micron or superficially porous particles, smaller particles essentially, which naturally give you higher pressures. They could be now achieved on these new systems. And many systems that you can purchase now can reach pressures up to 12 and 1,300 bar, depending on the manufacturer. So if we look at some of the theory behind why sub 2 micron works, we now have instrumentation that is able to achieve the pressures that are needed to use these particles. It's really because of the Van Diemer equation that that we get our improvements in chromatography. So if you look at your A term, your A term is your eddy diffusion. The eddy diffusion describes the path through the column which the analyte flows. It's directly related to the particle size and the packing efficiency, and it really doesn't have any contribution to the overall shape of the equation at all. If you look at the Van Diemer plot over here, your A term is flat across. It's consistent regardless of the velocity. It's all dependent on the efficiency and how the column was packed. If you look at your B term, then your B term is your longitudinal diffusion. And for the most part, that is negligible at normal operating conditions. There's obviously a very large dependency on the longitudinal diffusion out here at very low velocities, but this is not a usable velocity, so it's not important to us at all. And that's primarily because the molecular diffusion coefficient in a liquid medium is very small. And then lastly, the term that we will be referring to most today is the C term, and that's your resistance to mass transfer. And so the resistance to mass transfer is the most significant contributor to the overall shape of the curve. It increases linearly as the velocity increases. And depending on the particle size, the dependency on the velocity as a result or excuse me, the result of the plate height in terms of the velocity is affected either adversely or favorably. So the measure of column efficiency is based on the effective plate height. So you want really small plate heights. So you want to be operating down more in this region as opposed to this region up here. Small plate height equals higher theoretical plates. Your optimum flow, your optimum efficiency is oftentimes still at a very low velocity, not a very usable velocity. So oftentimes what we will do is we will sacrifice a little bit of efficiency and we'll move out into a more usable velocity. Overall, it doesn't affect the chromatography too much, but it does help speed your method up so that you're not waiting forever to get your compound separated and screened. So if we look then, we compare our Van Diemer equations for our different particle sizes. As I said, you want to be operating in this low plate height, high theoretical plate range. For our 10 micron particle sizes, there's this very steep dependency, and as you begin to crank up your velocity on your method, you're going to begin to lose your theoretical plates rather quickly. You don't have that happen as much for 5 micron, and 3 micron is definitely improved. But what you will begin to see when you start using your sub 2 micron, it's not always flat like this, but it's definitely flatter than the other 3 particle sizes. You can increase your velocity and you don't generally see any loss in the number of theoretical plates and the efficiency of the column. So if you have a separation and you're running at 1 mil a minute and it's a 10-minute method, for instance, you can probably increase your velocity by 2, decrease your method time by half, and still get the same kind of resolution as you would have on the slower method. And so it's about high throughput, getting more samples screened faster. This is where sub 2 micron really becomes an important tool in the chromatographer's toolbox for getting things screened quickly. If we go into some things to consider, I want to start with some misconceptions that I've read about a lot. I've heard customers mention in talking with them. And one that I hear quite often is that smaller inner diameter columns are the best. You'll see a lot of columns coming in at 2.1 millimeter inner diameter. Daicel, we have columns that are 3 millimeter, and then of course your more traditional HPLC inner diameters at 4.6. But smaller inner diameter columns are the best. It's not necessarily the case. This was a study that was published by Michael Dong in an article that he did, a review article. What you see here is you've got, this is just an Agilent C18 column. This is your 2.1 inner diameter column, your 3 and your 4.6 millimeter. And you can actually see your number of theoretical plates comparing the inner diameters is actually higher in your larger inner diameter column than it is relative to your smaller inner diameter column. Now, a lot of that has to do with heating gradients, which I'll touch on in one of the next misconceptions. But you can see, although smaller inner diameter columns naturally give you less solvent use, it might not actually be giving you the best chromatography. So Daicel kind of picked 3 as it's a compromise between higher plate count in 4.6, but you're not using as much solvent as 4.6, and you're still getting some savings on kind of both ends here. So I mentioned the heating gradients already, and so that's the next misconception. Longitudinal and radial thermal heating gradients are an issue. That's partly true. However, not if you have proper column conditioning. So this was a study that was done back in 2006, and it shows the difference in using a column heater versus a water bath. And in this case, it was an Acuity still air column heater. And it was a study at 25 degrees Celsius and 40 degrees Celsius. And you've got ACH, your heater, and WB, your water bath. So in all cases, you've got a better plate count when you're using a still air column heater. And that has a lot to do with the fact that the column heater kind of helps minimize the effect of the radial thermal heating gradients that results from using your shorter columns, your smaller particle sizes. The radial thermal heating gradients result in lower theoretical plates. So if you can figure out how to minimize the effect of those, you can essentially maintain your efficiency as you're pushing your column faster and faster. So the effect is quite dramatic when you get to some of these components like benzene and toluene. But the take-home message really is if you use the correct column temperature control, you can more or less minimize the effect that you would have in your loss of efficiency coming from radial thermal heating gradients. Now, the longitudinal thermal heating gradients actually don't have any kind of an effect on band broadening at all. In fact, a lot of times you will actually see your peaks sharpen because you're naturally, over the course of the column, going to be running it across effectively a temperature gradient. You will sometimes see a change in retention and in selectivity as a result of that increase in temperature. But there are a number of things that you can do to kind of counteract that. First off, you can use a longer column. And second of all, if you're running a method transferring it, say, from HPLC to UHPLC, and you ran your method on HPLC at 20 degrees or 30 degrees, just set your method for your UHPLC at 10 degrees Celsius less. And so it kind of overall counters the natural increase in temperature that comes with running at a higher flow rate and higher pressures. And then the last one that I'll mention briefly is that UHPLC provides higher sensitivity relative to HPLC. And that's also not true, assuming that you make a correction for the reduction in void volume that comes with your UHPLC. So this is from that same review article that Michael Dong published. This up top here is an Agilent 1200, and down below here is an Agilent 1290 UHPLC. This is a reverse phase gradient. It's the same sample on the top and the bottom. Only the bottom, which is your UHPLC, the overall concentration is adjusted based on the fact that you have a smaller void volume compared to your HPLC. And so other than the fact that you have these slight shifts in retention time, which naturally comes again from the fact that you have less void volume in your UHPLC, the overall signal intensity and the response is roughly the same, assuming you make that proper correction. So lower column void volumes result in higher peak heights. So just scale your sample accordingly, and you should obviously get the same response from both systems. So what sub 2 micron CSPs do we have available? As I mentioned before, we've got 39 different selectors. We've got 34 unique selectors. We have these 6 that are available. These 6 we have found in kind of our own studies, kind of cast a wide net over a lot of different types of compounds. So we have 4 amylose-based, our IA, ID, IG, and IH. And then we have 2 cellulose, our IB and our IC. So if you're going to be switching over from your traditional HPLC 3 micron or 5 micron particle sizes to your smaller sub 2 micron, you would want to make sure that your separation factors are the same, or you're at least not losing any separation efficiency by switching to these smaller particle sizes. So if we look at IA, for instance, we've got a couple of examples in normal phase and in reverse phase. This is alpha separation factor. So if you remember before, an alpha of 1 is considered separation, an alpha of 1.2 is baseline. So across the board, comparing your IA3 to your IAU under normal phase, you've got nice linearity, nice correlation, I should say, and your separation factors are either the same or actually improving. And the same is true in reverse phase as well for IA. If you look at ID, similar trend. You lose very slight efficiency or a very slight separation factor, but you're still maintaining baseline separation. For IDU in normal phase and in reverse phase, these were non-optimized methods, but you still have nearly baseline separation and good correlation between the sub 2 and the 3 micron. If we look at our Van Diemthers then, I was talking about Van Diemter plots. If we look at our Van Diemthers as they apply to IA in this case, for 5 micron, you see a very typical looking curve. As you're increasing in velocity, you're beginning to lose some of your theoretical plates. Your plate height is increasing. So if we use TSO as an analyte, trans-stilbene oxide, and we run this on a normal phase method, 9010 hexane IPA, you got a method of about 2 minutes. This is obviously a very good resolution, very good separation. Your plate count is just a little over 4,000 for 5 micron. Your flow rate is 0.4 mils a minute. If we jump to 3 micron, we can speed up our method, 0.6 mils a minute. We've cut our analysis time down to 1.2 minutes. And because we have our smaller particles and we have more efficient packing, we're now almost up to 7,000 theoretical plates. And making the jump one step further to sub 2, we can now increase our flow rate by 4 to 1.2 mils a minute. Our plate count is now approaching 8,500, and we've reduced our method time by 75% compared to the original 2 minutes for our 5 micron. So the savings, not only in time, but in solvent usage as well, are pretty obvious when you look at comparing these examples with TSO. And the same is true with ID. Again, this is TSO, cutting your sample analysis time down from 2 minutes to 0.5 minutes, and just about doubling your plate count at the same exact time. And one more example with IH. This method's a little bit faster, 1.2 minutes as opposed to 2 minutes, but it's still TSO. And now chopping it down to 0.5 mils a minute again. So The savings is there in cost. It's there for solvent time. It's there for improvements in analysis time. Theoretical plates, we already kind of talked about that a little bit, comparing between 3 and sub 2, but just a few more examples. These are now on slightly longer columns. These are 100 millimeter. The examples previously were on 50 millimeter. So the plate height naturally increases because you're doubling your column length, but comparing between 3 micron and sub 2 micron, you're at almost 10,000 plates more moving to sub 2. You can see the same thing for IB, going from IV3 to IBU. The same thing for IC, going from IC3 to ICU. For ID3 to IDU. And the last example from IH3 to IHU. So it's not just unique to one particular stationary phase. We're missing on this IG, but it's exactly the same for IG as well. So you kind of get the point. There's an improvement in efficiency and improvement in resolution that can be achieved in moving to your particle sizes. Well, one of the questions we get asked quite often is, so how easy is it to actually optimize your method going from 5 micron or 3 micron, which a lot of methods out there now are on those, moving to sub 2 micron? Is it possible? Is it easy? Is it straightforward? And it's actually quite simple. This case is for flavanone, very simple compound. This is a normal phase method, hexane ethanol. If you were to run this on IA 5 micron, this is a 3 by 150. Your analysis time's about 9 minutes. Making some slight tweaks just to the flow rate, you can now move to IA3 and you can shorten your column length to 100 millimeter. You're now down to 4 minutes. And if you were to jump to sub 2, and you can now shorten your column to a 50 millimeter, you've now cut your method down to 0.7 minutes. And you can see here, if we blow this up, you still have very good resolution, very good baseline separation between the two enantiomers, and you've chopped off more than 8 minutes. So imagine trying to do a large screening of a library of compounds, saving 8 minutes per run when you've got 6 different stationary phases that you're trying to screen. It adds up very quickly. And so the savings is kind of built in by switching. So let's go over a lot of examples. I promised a lot of examples, so let's go on those. This is a poster that we just presented last week, actually at a local chromatography forum. If anybody out there listening was there, you may have seen this there. Basically what we did was we took a whole bunch of 5 and 3 micron methods that we have in our application database, and we screened them on sub 2 micron just to see, again, how easy is it to transfer from 5 and 3 micron to sub 2, and then also to show kind of an overall reduction savings that can be achieved in making that jump. So I'll go through all of them quickly. I won't spend time on each one explaining it, but you'll get the general theme. So this is suprofen on IA3. So your 3 micron methods are in black and your sub 2 are in blue. So for suprofen, this is a normal phase method, hexane ethyl acetate with a little bit of TFA. You're decreasing your method time from estimate 8 minutes or so down to 4 minutes, or maybe just a little bit more than 4 minutes. So you're at 50% reduction, all while maintaining your good resolution, your good baseline separation, and essentially speeding up your time that it's taking you to do your analysis. This is an example where you actually had no baseline resolution on 3 micron, but by switching over to sub 2, you will end up getting a baseline resolution. Now, these are not optimized methods by any means, and so you might be able to achieve baseline resolution on 3 micron, but using very similar conditions without changing the mobile phase composition or anything like that, you go from no separation to good baseline separation. Show some examples on IB. So this is homatropine on IB3 to IBU. Big savings here, going from 9 minutes to your late eluting peak down to 3 minutes, so 66% reduction. And proglumid also on IB3 to IBU. Another example on IB3 and IBU. Guaifenesin now switching over to IC, so this is IC3 to ICU, going from 9 minutes, or say 10 minutes for this analysis, down to 4.5 minutes. Propafenone on ID and IDU. Naproxen now switching over to IG3 to IGU. Another case here where you almost have baseline separation, but not quite. And now you're achieving baseline separation with some little impurity in that sample there. And fenprofen. And going to this 2-hydroxypropanoic acid on IH3 and IHU. And then lastly, carprofen on IH3 and IHU. So you've got a number of different compounds we showed here, some acidic, some basic, some involving different types of interactions. You've got your pi-pi stacking, your dipole-dipole, and things like that. But if you were to look at your savings, comparing kind of the older 5-micron methods and your 3-micron and then your sub-2, moving from your 5-micron down to your sub-2, you're getting across the board here at least 50% reduction in analysis time, in usage of solvents, and in some cases you're approaching almost 70%. And again, these are not optimized methods, so it could even be 80%, 90% if you really push the system, which you can do on sub-2, because if you remember the Van Diemter plots, there is not a dependency on the velocity and the plate height like there is on these larger particle sizes. So these were all normal phase methods, as I mentioned. Same holds true if we look at reverse phase. So this is ibuprofen on IA3 and IAU in a reverse phase method. So again, here's an example of no resolution going to nice baseline resolution on our sub-2 micron. And this CBZ protected amino acid, norleucine, also on IA. 2-chloro-1-phenylethanol on IB3 to IBU. And hydroxime on IB3 to IBU. Again, another example where there was no resolution on 3-micron, but you get a nice resolution on sub-2. Hexabarbital on IC3 and ICU, and a CBZ protected valine on IC3 and ICU. What about multi-component reactions? Because up to this point, we've just been showing relatively straightforward 2-peak separations and antimeric separations. Sub-2 actually works really, really well on multi-component reactions. This example up top here is on IA 5-micron, 4.6 by 250. Your analysis time is, or your cycle time is about 17 minutes. You've got 8 different components in here. You've got 4 different sets of enantiomers. So if you go from your 5-micron 17-minute method and just jump down to 3-micron, you can increase your efficiency, improve your analysis time to 10 minutes. You can also cut your column length down to 150 millimeters, and then make the step to sub-2 micron IAU. You've now cut your analysis time down to 5 minutes. You've cut your column dimension down to a 3/100. So again, your solvent savings, your savings in analysis time. And if we zoom in to some of these later eluting, or even some of these that seem a little blobby, you actually still maintain good baseline separation for all of your components, switching from your larger particle size to your smaller particle size. We've got a second example here. It looks very similar, but the component mixture is slightly different. But going from your 5-micron, your 250 millimeter length column, down to a 150 3-micron, and then to your sub-2 3/100, effectively cutting your method time down from 40 minutes to 12, 13 minutes or so using sub 2, all while still maintaining good baseline separation between all of your components. And one last one for IH, going from IH5 to IH3, similar column dimensions, and then from IH3 to sub 2, going from 34 minutes down to 12 minutes, and again, still achieving baseline separation for all of your 8 components that are present in your reaction mixture. So this is quite powerful. Time savings, solvent savings. I'll keep reiterating that over and over again. And then we've got our 6 columns. So what can you do in terms of screening? These are all pretty well set in terms of your sample mixtures, but what happens if you just want to screen a whole bunch of different compounds? Well, let's take these 6 for example. You've got mefrucide, you've got, I won't say this one, and you've got narkidipin, you've got IA, IB, and IC, so all of these complementing each other in a nice screen. And then you've got on ID, IG, and IHUs, another 3 compounds shown here. In all cases, and you might have some separation, not quite baseline, but you have separation in others. Same goes here with nitridipine. You've got IDU where there's a separation, but not quite, but you've got a nice baseline separation on your initial screen. So all 6 columns together in a screening set make for a nice complementarity. You're able to screen all of these compounds at once. You're able to see how they react on all these different selectors, and you're able to cut down your analysis time compared to your 5 and 3 micron quite significantly. So if you put this all together, these are not the same compounds that you saw on the last 2 slides, but they are 7 similar compounds on 5 columns. The IHU is not included in here. But if you were to take all these and set them up in a screening, what would traditionally have taken you on 5 micron probably overnight at least, can now be done with conditioning between each run in under 5 hours. So this is 4.5 hours to do a screening of 7 compounds on 5 different stationary phases, which is quite remarkable. You can imagine if you're doing either drug design or target analysis, target design, you can screen through your library, your 96 well plate or whatever it happens to be, much more efficiently and much faster than you would have previously. The new trend these days is ultra fast separations, which they can certainly be achieved on sub 2 micron as well. Here's a couple of examples of some pesticides. This is furalaxol on ICU, less than 50 seconds. Devranol, less than 25, and anisoine, less than 25 as well. Benzolaxol and furoin, less than 25 seconds. And this was a case that was a little close to home to us, our affiliates over in Europe, Chiral Technologies Europe. There was a pesticide, fipronil, that was going around and happened to be contaminating some eggs. And so our column here, ICU, was able to do a nice analysis of that rather quickly, 15 seconds, which helped obviously increase throughput as you're going through and trying to test all of these different random samples from different egg lots and whatnot. Sub-second separations, getting close. Thalidomide, you might be familiar with thalidomide. Hexabarbital and Wineland-Mischler ketone, they're all approaching at least 10 seconds. Cavane and methobarbital and this imidazole at the end here. Certainly methobarbital in the center here has a lot of room for optimization and could probably get close to at least sub 5 second, probably getting close to sub-second. So there's a lot of good applicability. There's a lot of good things that can be achieved with our sub 2 micron columns. In addition to the brief introduction on chirochromatography, just a brief summary here of all the different topics that we touched on. Obviously, we talked about implementing sub 2 micron chiral stationary phases. Certainly requires some considerations, but translating from your older 5 and 3 micron methods to sub 2 is relatively straightforward as long as you take those things into consideration. There's similar selectivity and resolution, actually improved resolution compared to their 3 and 5 micron counterparts, um, as well as the improvement in analysis time and solvent savings. And the sub-2 micron stationary phases work well under a wide range of conditions. So it showed you normal phase, reverse phase, different pressures, different temperatures, very robust. They hold up very well to a wide range of conditions. And at the last couple of slides there, pointed out that they can be used rather easily for high throughput screening and ultra fast separations. So at this point, that concludes everything that I have for you. I know there's a lot of material, so we have questions coming up here in a second, but I am going to transfer you back over to Tracy so that she can give you a very brief wrap.
Thank you, Wes, and thank you, members of our panel, for answering questions. We hope you enjoyed today's presentation. Now I'm going to open up the floor for questions. Please use the webinar dashboard, click on the question section, and raise your hand so I can open your line so you can ask the question. Only one person is able to speak at a time, and please make sure your microphone is on, or if you have dialed in for audio, your phone is no longer muted. If you have any additional questions, please reach out to Dr. Umstead or to me, and we will be glad to assist you or point you in the right direction. Thank you all for attending, and please stay tuned for our next webinars in the series. July 17th will be achiral separations with chiral columns and DC Pack PBT and DC Pack P4BP columns. And then in October 30th, utilization of supercritical fluid chromatography with Daicel's chiral columns. Okay, we'll begin to answer questions in just a moment.
All right, so we have questions open now. We've got Heather Wang. Heather, you're on the line.
Yeah, can you hear me?
Yes,
Hello?
yep.
Okay, that's great. Very nice talk. I have a question. So what is the maximum pressure that those sub 2 microns column can tolerate?
So the pressure is really you're not so much worried about the integrity of the chiral stationary phase. We recommend for our sub 2 micron columns 700 bar as the maximum pressure. We have had people who have gone higher than that, but we can't necessarily guarantee lifetime. Like I said, it's not an issue so much with the integrity of the chiral stationary phase, but for overall lifetime, 700 bar is kind of what we recommend you operate at.
Okay, great. Thank you. There are
Yep.
another. I have another question,
Okay.
and on your example, and it looks like your there are a lot of time saving on normal phase, but reverse phase you only can save, improve the resolution.
Yeah.
I mean, doesn't save the time. For
Yeah.
for us, we are the screening lab. I don't know, high throughput, so we
Yep.
want to get the method as short as possible. I don't think the reverse phase doesn't looks like can improve the time saving.
Yeah, the examples that I showed, unfortunately, are mostly gradient methods. So if
Mm,
you were to transfer those over to an isocratic method, which most of the time we end up doing that anyway,
mm,
you might end up seeing, because those were all eluting quite late in the gradient, you
mm,
probably would end up seeing the expected improvement in the method time by switching to isocratic, and then based on that, you can probably push your flow rate a little bit higher to get the improvement in time and efficiency from the sub 2 micron. So that's a very good question. But across the board, isocratic usually works best, and so that would be a solution to that issue, just switching from gradient to isocratic.
But when you use aqueous, the pressure always is limited. So I don't think
Yes. Yep.
we tested your column, this U all the U column.
Uh-huh.
The, if you increase the flow rate, won't be the pressure limited. So
Yes. Oh
we
yeah. Yeah.
cannot get like a
Yeah.
normal phase, get a very short method.
Yeah, it's highly dependent on the viscosity of the mobile phase. In those
Right.
particular examples that I showed there, because they were eluting out farther in the gradient, there
Mm,
was a larger percentage of organic in there. So you might
mm.
not run into the same kind of issues with pressure, but it's certainly highly dependent on either the isocratic or the gradient conditions that you're using and the overall viscosity of the mobile phase. So that's unfortunately something that you can't really predict necessarily. If you see a separation on a very aqueous reverse phase isocratic method or gradient, then you might unfortunately you might not be able to push it and see the efficiency improvements that you'd expect to see, for instance, in normal phase. But that would be kind of a highly dependent on your compound or your sample. Um, so.
So you think those sub 2 microns Chiral column maybe good, where it's good, the best for normal phase, not reverse phase. For in the high throughput.
I mean, we've
You
seen we've seen it work very well in normal phase, reverse phase. We've seen it work really well in SFC, extended range. So, application-wise, internally, we most of our stationary phases work best on normal phase anyway. So that's generally
Mhm.
the focus where we do a lot of our examples. Our columns work well on all phases, but polysaccharides in particular work well on normal phase conditions. So it just happens to be that most of the improvements examples come from normal phase.
All right, good. Thank you so
Thank,
much.
thank you.
Mhm.
Yep.
Okay, so we have two questions.
So we have a couple of questions that came in through the answer board. We have one. Can I use sub 2 micron columns for both normal and reversed phase? Yes, you can use them for both. If you're talking about the same column, there is a regeneration process that we recommend you go through in switching from reverse phase back to normal phase. Basically, you need to get rid of all the water that's trapped in the column. So if that's something that you're doing, if you have, for instance, one IAU and you're using it for normal phase and reverse phase, we can send you the column instruction manual, which has that regeneration process that allows you to move back and forth. And then the second part of that question is it okay to use the same column switching between two modes? And I kind of addressed that already. Yes, as long as you are making sure that when you're going from reverse phase back to normal phase, you're regenerating it, or you're flushing it with THF to remove all of the water. We definitely recommend that you have two different sets. The immobilized columns are quite robust, and they do hold up well over time, going back and forth between normal phase and reverse phase. But in terms of the integrity and not abusing them too much, it's good to dedicate them to one particular phase and then keep them in that phase all the time. If you're in a pinch and you need to use one for the opposite phase, then certainly you can do that and you won't see any kind of negative effects from that. And that looks like that's all the questions that we have that haven't been answered. So at this point, we're going to go ahead and wrap up the webinar. On the screen now, you can see a couple of emails. Tracy pointed them out already. Her email address as well as mine. If you have questions, you can more than happy to follow up with you on those. And then we have a general questions line as well that you can email if you have questions, not necessarily about sub 2, but just chromatography in general. And then again, the dates for the upcoming webinars. So we appreciate your time and dedication and hope you'll join us in July.